Welcome to this explainer. Today, we're getting into a high-stakes, microscopic race that is literally happening billions of times a second inside your computer. As you already know, digital design is completely driven by a relentless clock, and every single piece of data has to cross its finish line before time runs out. But how do we actually know if our data is fast enough? How do we calculate those invisible delays? Well, today, we're decoding timing analyzers.
So what really happens when data loses its race against the clock? We know it's not just some minor glitch. That data is lost, corrupted, or overwritten. If even one bit is late to its designated register, the entire circuit completely fails. It's a literal race against time, right? And understanding exactly how to measure that race, that's the foundational secret to building high-speed digital electronics.
To figure out how timing analyzers calculate these delays, let's look at a basic physical problem. Imagine a standard logic circuit. We've got inputs on the left, passing through flip-flops, traveling through a few AND gates, and eventually landing in a final flip-flop over on the right. Now let's make a really simple assumption to make the math easy. Let's say the clock to Q and setup times for each flip-flop take exactly 1 nanosecond. And the delay through each logic gate also takes exactly 1 nanosecond. If you trace the longest possible path, from the input D at the bottom through 3 gates all the way to the final output, that path takes exactly 5 nanoseconds. Which brings us to a really crucial point, a 200 megahertz limit. Where does that number actually come from? Well, it's just simple math. Because our longest path delay is 5 nanoseconds, our clock period absolutely must be at least 5 nanoseconds long just to give the data enough time to finish the race. Divide 1 by 5 nanoseconds, and you get a maximum operating frequency of exactly 200 megahertz. If we try to run this specific circuit any faster than that, the data simply won't make it and the circuit breaks.
Enter the detective, the timing analyzer.
Now, counting gates manually is perfectly fine for a simple 5-gate circuit, like we just looked at. But what happens when you're designing a modern processor with literally billions of transistors? Obviously, you can't calculate that by hand. We need a tool that can instantly calculate these microscopic delays across millions of paths. So let's look at a real-world test case to see how this software detective actually works. Consider a schematic for a 3-number adder circuit. It's designed to take 3 8-bit inputs, A, B, and C, clock them into initial registers, run them through 2 adders, and finally store the result in a final sum register. It's definitely a bit more complex, and finding the exact delay through those adders isn't exactly something we want to just guess at.
But before we unleash our software detective on that adder, we need a quick refresher on the 2 main rules of the race. The first rule is setup analysis. This just determines if data arrives at a flip-flop early enough to be safely stored before the clock period ends. Think of it like a sprinter crossing the finish line before the buzzer sounds. If the data arrives too late, well, it violates the setup time and the race is lost.
But simply crossing the finish line isn't the only rule. The second rule is hold analysis. This checks to make sure that the data remains stable for a brief moment after the positive edge of the clock. The data can't just vanish the exact millisecond it crosses the line, right? It has to hold its pose for the finish line photo so it can actually be reliably stored.
So, how do we actually get our software to calculate these setup and hold delays? Well, in Quartus Prime, it's a very specific process. First, we tell the software to keep our specific register names intact during synthesis, just so we can find them later. Then we open up the compilation report, launch the timing analyzer GUI, and finally, we execute the report timing command. Now, keep in mind, by default, the software very aggressively assumes we want a clock period of just 1 nanosecond.
And that assumption brilliantly illustrates what happens next. When we look at the complete timing analyzer graphical user interface, which is basically our primary dashboard for investigating those intricate worst-case delays, we see the results. The tool has mathematically crawled through every single path in our 3-number adder. From the source flip-flops to the destination flip-flops, it calculated exactly how long the physical routing and logic gates will take. And right away, we can see a whole lot of red text, which obviously means we have a problem.
The concept of slack. To really understand what all that red text means, we have to talk about slack. It's really the ultimate metric of our digital race. Slack is simply the mathematical difference between your clock constraint, meaning the time you demanded the data arrive by, and the actual physical delay of the data path. Notice the really sharp contrast here. If you have positive slack, it means the physical delay is smaller than your constraint. The data arrived with time to spare. That's a total success. But if you have negative slack, your delay is larger than the constraint. The data arrived late. That's a critical timing violation and your circuit will absolutely fail.
Let's zoom back in on our software's diagnosis of that 3-number adder. Because the software used a default, completely unrealistic clock constraint of just 1 nanosecond, our circuit failed. You can see right at the top, we have a failing negative slack of negative 0.120 nanoseconds. The data from register B just took way too long to get through the adder and into the final sum register.
Let's break this math down again to really build our understanding of the circuit's actual speed. We can basically reverse engineer the timing analyzer's calculation. If our constraint was 1 nanosecond and we missed it by negative 0.12 nanoseconds, we just subtract the negative slack from the constraint. 1 minus negative 0.12 equals a real physical delay of 1.12 nanoseconds. That means the absolute maximum usable frequency for this exact adder circuit is 893 megahertz.
The software even lets us visualize this exact moment of failure. Looking at the waveform, the analyzer calculated that the data actually arrives at 5.65 nanoseconds. But, based on that aggressive 1 nanosecond clock rule we mentioned, the data was strictly required to arrive at 5.53 nanoseconds. It just completely missed the window and failed setup analysis.
The cure, setting realistic constraints.
Okay, now we need to shift from diagnosing the disease to actually applying the cure. We know our circuit physically takes 1.12 nanoseconds to process the math. But come on, we don't actually need this chip to run at nearly a gigahertz. We can fix the violation by providing the software with a much more realistic finish line. So here's the exact solution we're going to implement. We are going to relax that impossible 1 nanosecond default. We'll create a new clock constraint with a super comfortable 4 nanosecond period. Then, we'll write that constraint into a dedicated file, and finally, we'll tell the analyzer to regenerate its report based on our new, much more realistic rules.
Actually, creating this rule is super straightforward. We just name the clock, type 4 into the period box, and apply it to our clock node. But here is an absolutely critical detail. We have to save this rule. We save it as an SDC file, which stands for Synopsis Design Constraint. If you're working in this space, you know this is the industry standard language for telling software exactly how fast a digital circuit needs to be. Once that SDC file is saved, our previous timing report is officially out of date. The software is still stuck showing us the old 1 nanosecond failures. So we simply right-click the setup clock report in the interface and hit Regenerate. This completely forces the timing analyzer to instantly recalculate all the slack values based on our new 4 nanosecond boundary. And just look at the result. We have a victorious waveform. The data is still arriving at the exact same physical time of 5.65 nanoseconds. But because our clock constraint is now a much more relaxed 4 nanoseconds, the data required time has shifted outwards. We now have a massive, comfortable positive slack of 2.880 nanoseconds. The data comfortably beats the clock edge with plenty of room to spare.
The final step, recompilation.
Now, diagnosing and verifying timing is really only half the battle. Simply looking at a positive slack number in the analyzer doesn't actually change the physical silicon. We must recompile the entire design so the Corda software can physically optimize the layout around our new 4 nanosecond rules. To do this, we go into the main project settings, find the timing analyzer section, and we physically add our new SDC file into the project. This permanently attaches our 4 nanosecond constraint to the core of the design. Once that's locked in, we hit Start Compilation, and the software goes to work, literally rebuilding the circuit layout from the ground up.
And this brings us to a genuinely fascinating final result. After the full recompilation, we check our setup summary again. Our positive slack isn't 2.880 nanoseconds anymore. It's actually a slightly different 2.061 nanoseconds. Wait, why? Because during compilation, the optimization algorithms looked at our 4 nanosecond rule and realized they just didn't need to try so hard. The software made different, perhaps much more power-efficient physical routing decisions because it knew it had plenty of slack to spare. The delay calculation changed because the physical circuit itself changed. Which leaves us with this final, somewhat provocative thought. Mastering timing constraints isn't just about fixing annoying red errors on a screen. Timing constraints are quite literally the steering wheel for your compiler. If these constraints fundamentally change how the software physically routes and builds the circuit, what seemingly impossible designs could you achieve if you perfectly optimized your constraints? It turns out, how you define the race completely changes how the track is built. Thanks for joining me on this explainer, and keep questioning how things work.